Okay, this problem is coming from one of our homework assignments, assignment 19, I believe problem 5. So they give you a figure, and the figure shows a long straight wire near a rectangular current loop. Well, the current in the straight wire is 17. Well, again, these are my numbers. The current in the straight wire is going to be 17 amps, and it is a distance of 7.5 centimeters from the rectangular loop. The question is, what is the magnitude and the direction of the total force on the loop? Okay, so we're going to draw the figure that they gave us, where the red line represents the straight long wire. The gray represents the current loop, and the arrows are representing the direction of the current. I1, so the current in the long straight wire, is equal to 17 amps, and the current in the loop is 30 amps. And they tell me the length of the rectangle is 30 centimeters. Tell me the width of the rectangle is 10 centimeters. Okay, again, these are the numbers from my homework problem. Using the right-hand rule, I can then determine the direction of the magnetic field at the rectangular loop. Because your right hand would grab the long wire, then your fingers would then wrap around the wire in the direction of the magnetic field. So my fingers go into the page on the side where the loop is. So the green X's represent the magnetic field due to the straight wire. Okay? Well, R again is the distance from the long straight wire to the current loop. F1 is the force that the straight wire has on the first part of this wire, which will be pointing down, again using right-hand rule. Fingers go in the direction of the current, they bend in the direction of the magnetic field, and your thumb points in the direction of the force. So it points down for the wire where the current is going to the left, and it points up for the current that's going to the right. The rules also say, given two wires, both current flowing through the wires parallel to each other, if the currents are going in the same direction, it's an attractive force. If the current's going opposite direction, it's a repulsive force. So those also will give me a way of checking the direction of F1 and F2. So F1 and F2 are the forces on the wires parallel to the straight wire. Okay? So the question that we're trying to answer is, what is the net force on this loop? Concept we're going to use is the force on the parallel current carrying wires. And the relationship we're going to use, and we're also going to use net force. So net force is going to be equal to F1 plus F2 will give us the net force on the loop. For the concept force on a parallel current carrying wire, your book gives you the relationship in force per length. So that's why I have F over L. But that's going to be equal to mu naught being a constant, the current in one wire times the current in the second wire, divided by 2 pi times R, which is the distance between those two wires. So what's known is the current in 1, the current in 2, the length, the width of the rectangle, and R, the distance from the straight wire to the current carrying loop. What's unknown is the net force. So the plan is to start with the relationship net force is equal to F1 plus F2. What's unknown is F1 and F2. So the force F1 and F2 is going to be equal to F1 divided by L equal to mu naught I1 I2 divided by 2 pi r. F2 is going to be F2 divided by L is equal to mu naught I1 I2 divided by 2 pi. And in this case, R is going to be a combination of R, which is the distance from the long straight wire to the loop. But then I need to add on the width of the loop in order to get to the next parallel wire, which is that bottom wire. So I do R plus W, which is the distance, the total distance from the long straight wire to that bottom wire. Okay? Now both of these need to be solved for F1 and F2, so I multiply L on both sides to get F1 is equal to mu naught I1 I2 times L divided by 2 pi r. And this is for both F1 and F2. Okay, so both of these need to be solved for F1 and F2. Once you do that, then you'll have your values of F1 and F2, which you can plug into the beginning relationship. So the net force is going to be equal to F1 plus F2, which you're using the equations below to calculate F1 and F2. So I can now execute this and solve for F1. I get an answer of 4.076 times 10 to the minus 4 newtons. And then I can solve it for F2. Again, remembering to add on the width of the rectangle. And I get 1.747 times 10 to the minus 4 newtons for F2. So now I've solved for F1 and F2, and I can plug those back into the original equation. So the net force is going to be equal to 4.076 times 10 to the minus 4 newtons. And this is going to be negative because it's in a negative y direction. So if you go back to the original drawing, I do F1 going down, F2 going up. So F1 is in a negative y direction, F2 will be in a positive y direction. So I can add 1.747 times 10 to the minus 4 newtons. So my net force ends up being 2.33 times 10 to the minus 4 newtons. And it will be in a negative y direction. Okay, so the overall net force will be in a negative y direction, away from the long straight wire.